Okay, so now after covering joint distribution of two categorical discrete random variables, now we're ready to talk about continuous random variables. Okay, so we start with the definition. And as you could imagine, we're going to start with the definition of a joint PDF. Okay, so random variables x and y are jointly continuous if there exists a function. Okay, so here this function, of course, if you want to be super clear, you can also do this, okay, just to represent it's a joint. But if you put those like x and small y in the parentheses, that's already telling us this is a joint about x and y, okay? So if this PDF function, okay, well, later we're going to call it PDF, but now we know it is PDF. If it is non-negative, okay, just like what we had for the marginal case. And then also if you have a double integral, okay, of this joint PDF integrating with respect to x, integrating with respect to y on real line for both, okay, if it equals to 1, okay, then fxy, okay, is called, so I should have, okay, added those two up here, okay, it's called the joint probability density function of x and y, okay? So two things, okay, first of all is if we interested in finding out the probability of the x and y pair, right, in a particular region C, okay, and let's define C in R2, so because we're looking at 2 dimensions, right, so that is equivalent of doing a double integral, okay, of your x and y in C, okay, and then integrating of the joint PDF function and then dx dy, okay, so later you're going to see exercises, okay, and examples of how you can actually, once you have the joint PDF, how you can find certain probability of certain event, okay? So whenever we are encountering that kind of question, we always come back to this definition, okay, or this result here. The probability of x and y, the random variable pair, is in a region C is calculated by doing a double integral of x and y, okay, of the PDF function, the joint PDF, and then the range of what we're integrating about is x and y in this particular range that we're working with. And then, of course, another thing is the connection between joint PDF and joint CDF, okay? So if I want to get the joint PDF, okay, so A, B, right, each A is for x, B is for y, right? That is equivalent of saying, so this is going back to what we talked about in a couple of videos ago, that when you have this joint CDF, it's defined to be, right, x is small or equal to A and y is small or equal to B. Okay, so that if I looking at this definition one more time, then we'll see that if we do know the joint PDF, right, this is equivalent of integrating the joint PDF with respect to x from -infinity to 0 to A, and then with respect to y from -infinity to B. Okay, so this is the definition that we know before about the joint CDF, and now since we know the joint PDF, we can always do, for continuous random variables here, we can do the integration to get it, okay? And then lastly, okay, that connection is also the other way around, right? If I have the joint CDF, okay, then if I take partial derivative, okay, twice, one with respect to x, one with respect to y, then I will come back to my joint PDF. Okay, so as you can see here, and in those examples coming up, and also exercises that you're going to be doing, there are things that we will learn as new, right? For example, like here, how to do double integral. Okay, not everybody have taken, I'm sure, multivariable calculus, math 220 here or elsewhere. So we're gonna, the double integral concept was introduced in that class. But if you haven't taken it, don't worry, we're gonna go over that, and then specifically for the context of doing probability calculation. Okay, so we're gonna learn about how to do double integral. Okay, for those of you who have taken the course already, and then this will be a review for you. Okay, and then of course this is I guess for pretty much everybody, this will be more like a review because partial derivative. Okay, like taking, if I know the joint CDF, how can I get the joint PDF? I have to take partial derivative twice in this case. Okay, so we're going to see examples as well. So another very important property here, okay, is that if I have the joint PDF, okay, how can I get the marginal PDF? Okay, what we have learned so far for the discrete random variable case is that if I want to know the marginal distribution of, like, say, one of the variables, like the B and W, if you remember that example, B stands for black socks and the W stands for white socks, then if I want to know the probability, the marginal probability, right? So up there, we were doing, I think, something like this, right? And this is equivalent, like calculated by all of the possible W value, right? And then we are adding up, right? So we're sort of like trying to figure out the marginal of one of the variable that is the same as trying to fix the other, fix the one that we're working with, and then sum over all of the other ones. And that's how we define the marginal PMFs, right? If you remember, and then that is the name of the marginal here, the margin is because of the table that we can come up with. Okay, so here we have something very like a analogy, right? But then as what we're doing, as you know already, for anything with continuous random variables, we do integration instead of summation, okay? So here, marginal probability density functions are defined in terms of integrating out one of the random variables or integrating out the other one, okay? So for example, if I want to know the margin of X, okay, what I do is I integrate, okay, of my joint PDF, okay, I integrate out Y, okay? This is almost like what we have been doing, right, in the discrete case, right? You're sort of like summing over the other one, okay? And similarly, if I want to get the marginal of Y, I'm gonna do this exercises like doing the integral, okay, single integral here, okay, with respect to X, okay? So now let's look at an example, I think, so that we can put this into practice, okay? So let X and Y be uniformly drawn, okay, from the triangle below, okay? Find the joint PDF F, X, and Y, okay? So feel free to pause a little bit before you continue, okay, if you want to give it a try. We do show you the triangle here, and the key I would just highlight from the question itself is saying that X and Y, they're drawn uniformly, okay, from the triangle. Okay, so uniform, okay, so this is some kind of uniform distribution, okay? If you put this into context, this is saying that in this shaded triangle, okay, X and Y can be anywhere. Okay, so like could be here, that's an X and Y, could be here, could be here. So it's anywhere within this triangle, it could be drawn, okay? And it's equally likely at any point, okay? So this is a important starting point for solving this question, okay? So let's get started, okay? Because the joint density is a constant because of the uniform definition here, okay? Then what we can do, okay, this is very important, we can try to write out, right, the joint PDF, okay? And so if it's in this triangle, meaning that if X is greater or equal to 0, Y is greater or equal to 0, and X plus Y is smaller or equal to 3, that's this line, okay? So what we're doing, right, we're trying to create the bounds, okay, for X and Y, okay? And then if it's in this range, right, in this particular, I guess, like set, then it's a constant, okay? It's going to be 0 elsewhere, okay? So this is the setup, okay? Like we know, like as you know, like in the end, like the joint PDF in this particular example probably will always be some kind of like a different cases, right? Like say here we started off with a constant C for this range and for this set, and then 0 elsewhere. And then the next step, okay, is trying to figure out what that C value is. Okay, so C, as we know, it's a constant, as a placeholder for constant, but we should be able to solve it by the fact. So if I can bring us back into this one, okay. Don't forget, right, the definition of the joint PDF function, there is a requirement, right? If you need to have the joint, the double integral, right, dx dy of the joint PDF integrates to 1. Okay, so that's what we're going to use, okay, for solving this problem, okay? So just to get us started, one should be the, so here it's for anything that's just going back to the definition I showed you earlier, okay? Or I should say the concept, or like the constraint or condition, right? The condition that we need to get started. And then of course the rest becomes how to figure out the double integral, okay? So this might be new to many of you, so let's slow down a little bit. So what we're having here, the first step here, okay, is very generic, okay? It's a joint PDF, right? Integrating on the real line for both, okay? But then of course, if you look at this particular case that we have, okay, so we are integrating actually specifically for x is greater or equal to 0, y is greater or equals to 0, and then x is small equal to c, small equals to 3, okay? So with that in mind, let's like refine this double integral a little bit more. So this is maybe new notation for many of you as well. So the C, the PDF, right, it's a C, okay, in this range, right? And then we write all of the conditions we need in this particular double integral sign, okay? So I guess, yeah, so for this particular exercise, since it's a triangle, right? And then if you want to know, well, one thing, maybe like a shortcut here, is that you can recognize that the area, right, of this triangle, right? Because when I do the double integral, like say, when I bring the C out there, because C is a constant with respect to X and Y, so C is, you can bring it outside, right, of the integral. And then when you do that integration, okay, imagine like when you do this integration for this particular range, it actually just becomes the area, okay? Right, by definition, the area can be integrated, right, by doing a double integral, okay, on the x-axis, on the y-axis, okay? So in that case, this is simpler, right, to some degree, that we can maybe directly recognize that this becomes C times the area of the triangle, okay, which is C times 9/2, okay, which gives us C to be 2/9. Okay, so just to recap what we have done, okay, we first of all recognize that this is a uniform distribution, right? So we are, and in particular for this particular triangle, so we're able to start off of doing our two cases for the joint PDF, right? Like if it's in this set, we have a constant C that we're going to solve next, and then it's going to be 0 elsewhere or otherwise, okay? And then we use the fact that for the joint PDF, the double integral, right, of x and y of the joint PDF should integrate to 1. So we can use that effect, use that fact, and then try to solve this constant C, okay? And lastly, we'll recognize that this double integral of dx dy is really just the area of this triangle, so we can get a shortcut, I guess, in this case, that we're getting C to be 2/9, okay? And we also gonna see another example later, okay, related to this question, that we'll actually do a, I guess, a actual real double integral exercise, okay? All right, so to recap what we've done so far, the joint CDF of two random variables, okay, we know that this is by definition, okay, we write those subscript, and you notice that sometimes I don't, sometimes I do. Well, I guess I should do better, like try to keep like the subscript everywhere whenever we're doing it. But a lot of times, as you can see, whatever is going into the parentheses already shows us that whether this is a joint or this is a marginal or whatever, okay, or a conditional, right? That's another possibility. Anyway, so the joint CDF of two random variables for any type, right? You can have discrete, you can have continuous. It's defined in this way, okay? And the probability of this x and y in a rectangle, if you ever wanted to know about that, okay, you can have another. So I guess this is something new, but it's pretty overall straightforward, as you could imagine. If we do a sketch right over here, and then if I try to do like, let's just say x1, x2, right? And then let's just say y1, y2, right? So, well, the probability of this triangle, right, is going to be this triangle, right, by definition. And then if we use the joint CDF definition down here, if you work out the math, I think this will be true, okay? So you can try to verify that to make sure that it makes sense to you, okay? And also the marginal CDFs, right? The marginal CDFs is recognized by taking the other one as whatever the range it could be. Okay, so fx is fxy when y is taken as infinity, right? In terms of the CDF definition, because it's this represent the probability of x equals to x, right? And then y is smaller equal to y for the continuous for the discrete case. Okay, and similarly you can do that for the y as well. Okay, and the other things that we have talked about is the joint distribution. Okay, the first one we talk about is the joint distribution of two discrete random variables. Okay, so we are able to get the joint PMF. Okay, defined to be the probability of x equals to x and y equals to y. Okay, and then the marginal, as now we know, to get px. Okay, we're summing over the joint PMF, summing over all of the possible y value. Okay, and similarly, I do that for y as well. Okay, and then the concept of joint distribution of two continuous random variables, we have the joint PDF definition. Okay, those requirements, right? You need to have non-negative joint PDF, and also the double integral, right, of the joint PDF should integrate to 1. Okay, and then of course, if you have the probability that like a set of probability that you want to compute for, then if you have a set in R2, okay, then this probability of x and y, this pair in this set C should be a double integral of the joint PDF function, right, within this set. Okay. Lastly, marginal PDFs, just like the marginal PMFs. Back there, we're doing summation of the other one. Down here, we're doing integration over the other one. Okay, so think about it as integrating out. Okay, then you'll be able to get it. Okay, all right. So this exercise, okay, is related to, like I said, the earlier exercise of finding that C, right? But this is what I mean by a real double integral exercise in some sense. Okay, so let's slow down a little bit. Well, sorry, this one is not yet, but next one, sorry about that. Okay, so the marginal PDF. Okay, so this is coming back to this definition, right? We know that the marginal PDF should be done by integrating out the other one. Okay, so let's see how that can be done in practice following that example of the triangle. Okay, so this is what we have saw before, right? So we have C equals to 2/9, so that's all good. And then now the goal is to find the marginal PDF. Okay, so the marginal PDF. So first of all, okay, whenever you're working with a PDF or anything, you want to specify the range of that random variable. So for us, x is what? X is from 0 to 3. Okay, so keep that in mind. Whatever we're doing with it is conditioned on the fact, okay, that x is between 0 and 1. All right. So how am I supposed to do this not double integral, like single integral of integrating out y, right? So that's what we know. So this is starting with the definition, right? In order to get the marginal, I need to integrate out the other one of the joint. Okay, so now the question becomes, okay, I know my fxy, right? Within this range is 2/9. Okay, I need to integrate out y. Okay, what would be, so of course, when we started off, we're just writing like on the real line, right? But we can refine it a little bit given what the question is doing. Okay, so dy. Okay, so first of all, I guess this is 2/9. Okay, so that's all good. Okay, and now I need to integrate with respect to y. Okay, so what that does, if you think about it, is that we need to find the range of y under this condition. Okay, so first of all, let me use a different color. Okay, y is greater or equal to 0. Okay, so the lower bound is 0, I think. Okay, so that should be easy. Okay, the upper bound, let's be a little bit careful. Okay, so we know that y can go from 0 to 3. Okay, but well, that's, I guess the 3 is the upper bound, right? But it is the correct upper bound for this. Okay, that's my question here. Okay, so notice that y is from 0 to 3. Okay, but at the same time, don't forget we have a third and very important constraint here. Okay, x plus y should be smaller or equal to 3. Okay, so think about this. Okay, so what we're doing right now is that we're trying to find the marginal PDF of x. Okay, so whatever you're doing, right, after you do this single integral, okay, one thing to keep in mind is that, well, y needs to be gone, right? You have to integrate out y, okay? And since it's a PDF about x, okay, it could be a constant, okay? It could also be that x is involved, okay? So that's another way to check your work and then make sure that things are right, okay? So let's see what is the new range here, okay? So the new range, okay, so first of all, this is 2/9, okay, and then it's dy, that's good, okay. The lower bound, I was talking about it, right, should be 0, okay, that's what it is, okay. The upper bound now, okay, is 3 minus x, okay. It's not 3, because 3 is indeed the maximum possible value for x, for y, right? But at the same time, don't forget, we're conditioning, okay, on the x value, whatever x value that we have is between 0 and 3 here. So conditioning on that fact, or given that x equals to x, small x here, then y cannot go above 3 minus x, okay, because of this constraint. All right, so keep that in mind. Okay, this is very important and probably new to some of you maybe, but regardless, we are going to try to practice and then make sure that we're getting this right. Okay, so this is also just a note, be careful about the range of y given x equals to x. Okay, so again, we're looking at x in this range, okay? So we need to be careful about the bounds, okay? And then lastly, we write it together in one thing, okay? We're just having fx, okay, equals to 2/9 times 3 minus x when x is between 0 and 3, and then 0 otherwise. All right, so this is a application, right, of doing, once you have the joint, right, you are trying to get the marginal. I'm just trying to come back to this slide, okay? And then of course you can do that for wide if you want, okay? And I think that's actually exercise for the live session. So you will get the practice for that, okay? And all right, so that's one kind of application, right, of what we know about the joint, joint PDF, right? The other kind of exercise that, or example that I'm going to show is about this kind of application, okay? So, well, now if I know the joint PDF, right, if I want to know a particular probability of a particular event, okay, we're saying that, well, you're integrating, right, with respect to x and y, dx, dy, but then of course you have to do it in the particular range for the set that you're working with. So let's look at an exercise here, which will involve, like I said, a real double integral exercise, okay? So let me slow down a little bit, okay? In this previous example, find, okay, probability of this event, okay? So this is like that C that we're talking about, okay? But then of course, in context, it could be a little bit more concrete. So in this case, the C that we're working with is x is smaller than y, okay? And I do include a graph for you to visualize what we're doing, okay? So remember, this triangle was where x and y was uniform on, okay? They're uniform on this triangle, okay? But now, and we solved, right, 2/9 for it, and earlier the other exercise we did the marginal integration, that's a single integral. Here is a double integral because we are finding a probability of an event about x and y at the same time, right? So we know that we'll have to do a double integral, okay, with respect to x and y, so it's dx dy, right? And then of course the double integral has this constraint of what we were writing generically, right? X and y should be in that C range. Okay, so now this is our C. So how can we express it? Okay, so to get us started, okay, the C region, okay, is this shaded area, okay, because, well, we still have, right, x and y, right, like x between 0 and 3, y between 0 and 3, and then of course also the x plus y, right, needs to be smaller or equal to 3. Okay, but furthermore, okay, this region is smaller than that bigger region because we also need to have x's smaller than y, right? So this region, if I write it out, and I highly recommend you to try this out for any other exercise of this type as well, right? You identify the region and write it clearly out because you're going to use it later on to figure out the bounds for your integral. Okay, so x is greater or equal to 0, that's good. Y greater or equal to 0, that's good. The sum is smaller than small equal to 3, that's what we know already. And then lastly, x is smaller than y. Okay, so with all that in mind, we are ready to try to do a double integral. Okay, so this is definition. Okay, we know that. if I want to know the probability, okay, of x smaller than y, that is an event, right, about x and y. So you are doing a double integral, okay, C, we're going to define it, or like we defined it already, but then we're going to try to work out the double integral bound soon. But going back to the definition, we know that this is the first step, okay? All right, now probably the most challenging part. Let me slow down here a little bit, okay? This is trying to figure out how you're gonna do the integral, okay? So I was doing it, you can do it either way, okay? Like say whether you want to do dx, dy or dy dx, okay? I'm doing it of the dy dx format just to as an example, okay? And so here, for example, okay, what we're doing is that, well, this is 2/9, okay? So that's all good, okay? And if I'm doing dy first and then dx later, okay? So what this does is that, well, there are it's a double integral, right? So we need to figure out the bounds for both, okay? So the bound, okay, so maybe the easier one, okay, is to do the outer one first, okay? The outer one, if I look at the range of x of this area, what it should be, okay? It should start from 0, right? Okay, and it should end at the middle point, so not up to 3, okay? Only gets here, okay? So this is going to be 3/2, okay? So that's why for x, is integrating from 0 to 3/2. Okay, so that's good, and we can keep that aside. Okay, in the inner one, okay, we need to do dy. Okay, and dy again, if you remember the example that we saw earlier, trying to solve the like the marginal of fx, right? We need to think about when we're integrating out y, we need to think about the bounds of y in terms of x. Okay, so let's look at this area one more time. Okay, the lower bound. Okay, if I look at, let me actually just erase this part, so it's probably easier for me to do this one more time. Okay, yeah. So if I look at this area, okay, we know that it is this area. Okay, so in terms of y, okay, if I look at the lower bound of y, okay, it's going to be this line. Okay, because y always needs to be greater or equal to x. Okay, so that's why my lower bound here is x. Okay, and then the upper bound, okay, is this one. Okay, is the upper in terms of y, right? I'm looking at lower y. So if you think about upper and lower, right? So this line we know is 3 minus x. Okay, so that helps us to determine the bounds of y. Okay, so again, this is doing dy dx, right? So we first of all figure out dx, and then dx we know that is really just about the range of x. Okay, and here, as you notice that, well, because this is the outer integral and we're trying to get a probability, right? So the bounds that you have for the outer integral should be some kind of like values that you're doing, right? Cannot be like anything about y anymore. Like you should have integrated out y in the first place, in the middle, in the inner part. Okay, so that's another way to double check your work, your dx. Okay, or like the outer one should be integrating the bounds for it should be some kind of values that you can get, not in terms of the other random variable. Okay, and then the inner one, like we said, okay, is doing dy, right? So we need to express the bounds for y in terms of x. Okay, so the lower bounds is this lower line, okay? The upper bound is the upper line, okay? So essentially when you're doing the integration, what is this doing, right? Like if you think about from x to 3 minus x in terms of dy, we are integrating like this line, right? All of those infinite number of lines of getting the difference between those two. Okay, so that's another way to think about how the integral is doing. Okay, all right, so with that in mind, okay, the rest hopefully is mostly just like simpler calculus. Okay, we're doing it one by one. We evaluate the inner one first, which is a constant, so that's easy to do. And then the outer one, we do need to recognize the integral of it a little bit, and then eventually you're gonna get the probability to be 1/2. Okay, so I won't talk about like the details of the rest. I don't want to make the video too much longer anymore, and too much longer from now. Okay, I think it's already pretty long. But regardless, I would just highlight that whatever I was saying earlier here, right? I was saying, well, when you're working with the double integral, you can do dx dy or dy dx. Okay, we chose, or I chose to do dy dx. Okay, because it's actually easier to do. Okay, for if you're interested, okay, feel free to try a version of dx and dy. Okay, so that requires you to think about the range of y from the outer integral, right? So that will be from 0 to 3. That's all good, okay? If I do dy, okay? And then I need to do a dx within it, okay? The inner one is 2/9, we know because of the joint PDF, right? But then my question for you is that how am I supposed to find out about the range of x in terms of y? Okay, so in terms of y, you need to think about the range of x. Okay, so one thing I will just give a hint for you is that you actually will need to break it into two integrals to do this, because when you have x, so like when your y is from 0 to 3/2, then you have this particular range for your x. Okay, so the range of x, I think in this case, the upper bound and the lower bound is like this two. Okay, whereas when your y is between 3/2 to 3, then you're doing the upper one, right? So I'm going to use a different side, okay? And then the bounds are different, okay? So that's why. So feel free to try it out, but like I said, it will be more challenging, I think, for this particular case to do dx dy, and that's why we choose this dy dx as the example, or I should say, as the approach, okay? Alrighty, so all of this hopefully is good, okay? And then we saw the exercise, right? One exercise of doing this, okay? And then lastly, the joint CDF, right? This is again a recap. The joint CDF, we know the definition, and then of course, if you want to get the joint PDF from it, you take a partial derivative of 1 by 1, okay? And then eventually also the marginal PDFs can be obtained by doing single integral, okay, integrating out the other variables.